In this video, we'll explore strategies for predicting whether a reaction will follow the SN1, SN2, E1, or E2 pathway. We'll review key factors that influence each pathway, including leaving group ability, substrate structure, nucleophilicity and basicity of the Lewis base, and solvent effects. Finally, we'll connect these pathways to the first reaction we learned, alkane halogenation, recognizing how these mechanisms interconnect and build upon one another. Substitution and elimination reactions typically occur at tetrahedral sp3 hybridized carbons bonded to good leaving groups. Leaving group ability is determined by the pKa of its conjugate acid. The lower the pKa, the better the leaving group. Without a good leaving group, a reaction may not proceed regardless of other contributing factors. When a good leaving group is present, the reaction mechanism depends on several factors, including the sterics of the substrate, the nucleophilicity or basicity of the Lewis base, and solvation effects. Let's break down each of these factors to understand which conditions favor specific reaction mechanisms. Step 1 is to identify whether the alpha carbon of the substrate is methyl, primary, secondary, or tertiary. After confirming that the leaving group is suitable, we should then evaluate the steric hindrance of the alpha carbon on the substrate. Sterically hindered alpha carbons and beta branching discourage SN2 reactions, as the rate of SN2 reactions increases with less substituted alpha carbons. With just the information about the substrate and the presence of a good leaving group, we can establish some general guidelines. For a methyl substrate, the reaction will proceed via SN2. If the substrate is primary, it typically favors SN2 unless a strong, bulky base is present, which could lead to elimination. Secondary substrates require more information, as SN1, SN2, E1, and E2 mechanisms are all possibilities. For tertiary substrates, SN2 is ruled out due to steric hindrance, but SN1, E1, and E2 mechanisms remain potential pathways. By considering the substitution level of the alpha carbon, we can narrow down which reaction mechanisms are most likely to occur. Step 2 is to identify and evaluate the Lewis base participating in the reaction. This can help us separate out SN2 and E2 from SN1 and E1 pathways. If the substrate is primary, the reaction typically proceeds via an SN2 mechanism, unless the Lewis base is both strongly basic and bulky. The nucleophilicity of a Lewis base decreases with increased steric hindrance, while its basicity may remain high or even increase. A common example of a bulky base is tert butoxide, which is strongly basic but poorly nucleophilic due to steric hindrance. When reacting with tert butoxide, the reaction favors E2 over SN2, leading to the formation of the less substituted alkene product. For a secondary substrate, if the nucleophile is strong but weakly basic, the reaction generally proceeds via an SN2 mechanism, especially when carried out in a dipolar aprotic solvent such as dimethyl sulfoxide, DMSO. If the substrate is secondary and the Lewis base is strongly basic but weakly nucleophilic, the reaction tends to proceed via an E2 mechanism. When the substrate is secondary and the Lewis base is weakly nucleophilic and weakly basic, the reaction may proceed through SN1 and E1. Because these two mechanisms share the same carbocation intermediate, they are almost always in competition. For a tertiary substrate with a weakly nucleophilic base, the reaction proceeds through SN1 and E1 mechanisms. If the substrate is tertiary and the Lewis base is strongly basic but weakly nucleophilic, the reaction is expected to proceed via E2. The last factor to consider is the solvent. In SN1 and E1 reactions, the nucleophile often doubles as the solvent. Polar protic solvents, such as water or alcohols, are poor nucleophiles themselves and can stabilize nucleophiles through hydrogen bonding, which decreases their reactivity. For secondary substrates with a good leaving group and a weakly nucleophilic nucleophile, dipolar aprotic solvents such as dimethyl sulfoxide, DMSO, generally favor SN2 reactions. These solvents enhance the nucleophilicity of many anions by not stabilizing them as strongly as polar protic solvents do. In general, SN2 and E2 reactions are favored in dipolar aprotic solvents, whereas SN1 and E1 reactions are favored in polar protic solvents. Here is a helpful table for deciding on the reaction mechanism, summarizing the factors we just discussed. Let's wrap up by discussing how all the reactions we've covered tie together. We began by studying alkanes, which are generally non-reactive but serve as the backbone for many organic molecules. We explored how to functionalize alkanes through free radical halogenation, where a halogen replaces a hydrogen atom on the alkane. This process introduces a halogen which acts as a good leaving group, making the halogenated alkane susceptible to various substitution and elimination reactions. These reactions facilitate the interconversion of different functional groups, a foundational concept in synthesis. Understanding this functional group interchange is crucial, as much of the upcoming content in this course builds upon these principles, highlighting their importance in the broader context of organic synthesis. As always, let's do some practice. Show how to carry out the synthetic conversions indicated in an efficient manner. Find as many other interconversions as you can. If more than one step is required, show the products for each step. Feel free to pause the video and try these problems on your own first. In the first transformation, the propane starting material is converted into an allylic ether. Let's propose the steps to carry out this synthetic conversion. We know that we can functionalize alkanes using free radical halogenation. The two radical halogenation reactions we've covered are chlorination and bromination. Chlorination is less selective, so treating this propane starting material with chlorine under photochemical or heat conditions will produce both 1-chloropropane and 2-chloropropane. Bromination, meanwhile, is more selective for the more substituted position, which is more suitable for our transformation because it selectively yields one product. The secondary bromide product that we obtain can be treated with potassium tert-butoxide in a dipolar aprotic solvent or in butanol to form propylene through an elimination reaction. The propylene can then undergo allylic bromination using NBS with peroxides under photochemical conditions carried out in carbon tetrachloride. This allylic bromide can then react with sodium methoxide in dimethyl sulfoxide to undergo an SN2 substitution, yielding the final product. In the second transformation, the propane starting material is converted to a secondary iodide. We have not covered substituting an iodide in place of a hydrogen through radical halogenation, so we can infer that a halide, such as a bromide, was present at the secondary position and subsequently replaced with an iodide through a substitution reaction. We can begin this transformation by treating the propane starting material with bromine under photochemical or heat conditions to form 2-bromopropane, which can then undergo nucleophilic substitution with potassium iodide and dimethyl sulfoxide, DMSO, to yield the product. In the third transformation, the propane starting material is converted into an alkyne. We can start by treating the propane with bromine under photochemical or heat conditions to produce 2-bromopropane. This intermediate can then react with an alkyne nucleophile in DMSO through nucleophilic substitution to form the desired alkyne product. In the final transformation, propane 1-diazonium is converted into a thioether. The diazonium ion in the starting material is an excellent leaving group, enabling reaction with sodium ethyl thiolate in DMSO to produce the thioether. As always, thank you for watching, and I'll see you next time.